This is the 8085 microprocessor. As we see, we have a set of registers, 8-bit registers called B, C, D, E, H, and L, alongside A and the 8-bit temp register here. Some people show these registers as 16-bit register pairs like B, C, D, E, and HL, but in here we show them as 8-bit. The reason is because we have an 8-bit internal bus. By 8-bit internal bus, I mean that we have 8 wires throughout our chip, which is used for transferring data between one register to the other. Why do we need to transfer data from register to register? It's because, for example, we have the ALU, the arithmetic and logical unit, used for doing those kind of operations, which would take 2 inputs. The inputs would come from the A register and also the temp register. So let's say that we want to add 2 numbers, which those data are inside the memory. You would first try to fetch those numbers and put them inside, for example, B and C register, and then we move them to these 2 register, which are the input of the ALU, and then the control unit would issue the addition and this operation or other kind of operation. The operation would be done, and based on the result, the 8 bits inside the flags register would be changed. Why they should be changed? We have some kind of instruction like jump, carry, or other kind of jump, which are used for implementing the statements in the, how you see in the statements in the high level program, like if and else. How do this if and else happen? Well, at the low level, it's like in the program it's like this, that jump carry, that if the carry bit is set, then jump to a specific location, because at the end of the day you see that all the program does is that some conditions are checked. If those are met, then it would jump to a specific location. It would jump, execute some kind of instruction. If it is not met, then other kind of instructions would be done. So these instructions would have some specific address as these instructions. So this if would have a condition that if it is met, these kind of instruction would be done, that the address of this instruction would be put inside the PC register, which is a 16-bit register. So the flag register, one of its bits is called the carry bit. That the jump carry, one of the instructions of the 8085 microprocessor, works like this, that if the carry bit here is set, then it would jump the value that comes as an argument for the JC instruction would be put inside the PC. Therefore, what the CPU does is that if some specific bits inside the flag register are set, a new value, a new address would be loaded inside the PC. So when the current instruction has been executed, then an instruction at another location would be done, and therefore implementing the if and else. So these are the different registers that we talked about. Other than that, we have the SP and PC. PC we completely talked about, but it is 16 bits long. Using 16 bits, we could address 2 to the power of 16, which is equal to 64K. What the CPU does is that it would just put the value inside the PC register on the address bus that we talked about in the previous lecture. So the value of the PC would be put inside on the address bus, which just goes to address the our memory, and then the control signals would be issued, and the related data on the corresponding memory cells would be put on the data bus. So if it is 16 bits long, then the address bus should be 16 bits, so that this value would be put on the 16 bit of the address. Now this would be explained later. What do we mean by 64 kilobyte of memory as other things? So if you don't understand what I said so far in this lecture, it's completely okay. We would go in detail about all of these building blocks. But other than that, we have the instruction register, which is also 8 bits long, and we explained that as well. SP is 16 bits used for pointing to the top of the stack. In here we explained that sometimes we need another program to be executed, so the value of the PC would be changed to the address of the first instruction of the second program. But after the execution of this is completed, we need to get back to where we left off. So somehow before we jump to this location, we need to save the address the last address of the current program. So this address should be saved in another place in the memory. How do we retrieve it after the next program has been executed? By just having a specific register called SP, which always points to that location, which we have a memory structure called a stack. It was just one of the applications of the stack that I explained. The reason is that I wanted you to just feel some kind of need for that. So SP and PC, both of them just point to some specific locations in memory. By pointing to, I mean they contain the address of some location in memory. So other than that, we have the IR, and these two are the control unit, which we said they would just look at the instruction register and check that with a table to figure out if the pattern just match a specific pattern to issue the corresponding signals to execute a instruction. This interrupt control, let's imagine that we have a keyboard and currently the CPU is executing a program, and we want the CPU to that whenever the user presses a key on the keyboard, well, obviously we need the CPU to do something else. The user just pressing a key on the keyboard. So what we do is that we connect that keyboard to one of the pins here, and the way that they work is that if any one of these pins go high, then the specific address would be written on to the PC. So when the current instruction is executed, then the CPU would jump to that location. So our job is this, that first we write a program that we want to handle whenever the user presses a key. Then we put that program in a memory location, starting at the memory location in RAM. For example, 100, that starts from the address of 100. Then when the user presses on any key, because it is connected to one of the pins of the CPU, that pin would go high, that the address of 100 would be written on the PC. Then the CPU would just look at the address of 100, which is the program that we wrote to handle that interrupt. That program would be called interrupt service routine, or ISR, a program that we write to handle a specific interrupt. An interrupt is just just based on what we said, it's just telling writing some new value inside the PC register. So let me check if we have other things to say. Again, we would go through all of these things one by one and in detail. But lastly, we want to talk about these wires in the next lecture. We said that if we want to fetch some instruction, we put the value inside the PC register or SP register on these 16 bits, on these 16 wires, to just fetch some instruction or some data which would be part of another instruction. So we need 16 wires to transfer those addresses, but also we need to transfer the data. We need some wires to transfer the data after the memory cell in the memory has been addressed. This data in the 8085 microprocessor is 8 bits long. Architecture of any CPU is usually defined, well, is always defined by the length of the ALU, which in this case just happens, the A register happens to be the same with the ALU, because one of the inputs of the ALU is a register. So when we say 8085 microprocessor is an 8-bit microprocessor, we mean that the length of the ALU is equal to 8-bit. We need that at each clock it could just do one 8-bit operation. Again, we would get just to all of them later. But if we say that currently the tablet that I'm using to record this lecture is a 64-bit microprocessor, it means that the length of the ALU of my microprocessor is equal to 64 bits, which happens to be the length of the A register as well. So the A register of the tablet that I'm using, and most likely any device that you are using to study this lecture, the A register of it is equal to 64 bits. It could save 64 bits of information. But we have only 16 bits of only 16 wires here, which based on what we said, we need 16 bits to transfer the data, transfer the address and we need 8 wires to transfer the data. So this should have been 24, 16 for address and 8 for the data, but it's not. These 16 wires are what we say multiplex to be used for both address bus and also the data bus. First, we need to address a memory cell inside the memory. Then we just then we work with the data bus. So at the same time, we wouldn't need both of them at the same time. That's why first we would use these 16 wires as the address bus. When the memory cell has been chosen, then we use 8 of these wires as the data bus. So in the next lecture, we are going to completely talk about them. Also, these arrows that I'm showing here are just abstractions. Inside them, it would be actually wires. So if we zoom in, when I'm just showing these 2 arrows, these are actually 8 separate wires, and each wire could have a low level voltage or high, which we show them with 0 and 1.